Today we're going to talk about the power rule, and we're going to build off of what we learned in the first class, realizing that the derivative we can find by finding the slope of the tangent line. Now, as we go through this, there's a couple of things that we're going to need to know. When we talk about taking the derivative, there is notation that we use. In fact, there's two kinds of systems that are commonly used when finding the derivative. So if we're starting with some function, say y is equal to f of x, some function, when we want to say we're taking the derivative, we use these special symbols. The first one, the f with the little hyphen, or excuse me, f with the little dash up top there, or the apostrophe of x, that is said as f prime of x. That means the little prime notation there, the apostrophe, means you're taking the derivative of the original function. The second notation, this d over dx, is said as the derivative with respect to x. I have the two equal to each other simply to represent that they mean the same thing. F prime of x is equal to the derivative with respect to x. You'll notice that when you're doing this, the derivative with respect to x of the function f of x. So when this appears in your book, you'll know that it's referring to the derivative. The original function would be here, and then of course it set it equal to something and say what the derivative is. And the other one, you just simply put f prime of x equals, and then you put what the derivative is as well. One of the unique things, I should say, this f prime of x is referred to as you might guess, the prime notation for referring to a derivative. This notation is the Leibniz notation. And besides seeing it this way, meaning that what this is equal to is the derivative, it's also used as a command. So it tells you that when you see this, you're going to take the derivative of this. And in fact, in the homework, any test or quiz, I could simply put this derivative with respect to x of f of x and nothing else. It simply tells you that you need to take the derivative of the function after the derivative with respect to x, the d over dx. Now, we were working yesterday, or the last class, saying that the derivative, if we want to find the derivative at any point on a curve, we graph or plot the tangent line at that point. And again, the tangent line touches just at that point. So here we have the function y equals 1 over x, and we want to find what the derivative is when x is equal to 1. Well, I already have the line drawn here. As we look at it, we realize, oh, well, here, if we wanted to find the derivative at x is equal to 1, at this point here, we draw the tangent line and figure the slope of the line, and it's the derivative. It's the same thing. Well, we notice that it crosses here, and there, so it seems to be a slope of minus 1. If we start, we come down 1 on the y and over 1 on the x. The change in y is 1, the change in x is 1, and it's going down, so the slope must be negative. So we'd say that f prime of x equals 1, or the derivative equals, minus 1, or f prime of x is equal to minus 1, or the derivative of x is equal to minus 1. Now, this particular method works, but it has a few drawbacks. What if, when I drew this, I had my ruler placed just a little bit off? Just a small amount. It's still, if x is equal to 1 here, it still looks like I'm drawing the tangent, but when I look at it, we know it crosses there. It doesn't cross there like it should. It doesn't, there, it finally does. So now when I try to find the slope, I'm going to say, well, the change in y, the y goes from here up to here, to here, down from here. So we come down and say 1, 2, 3, 4, 5, and the change in x comes from here over. 1, 2, 3, 4, it's going down. So we would say, well, the slope, or the derivative, is equal to minus 5 over 4. Well, which one's correct? Did I actually draw it incorrectly the first time and correctly the second time? Well, as I mentioned, I actually did draw the second one off, knowing that it was off. So the second one is wrong. But what if you had to do this regularly? You're going to make a small mistake somewhere. And even a small mistake will make the derivative incorrect. Or imagine if you're working for a company that's auditing 100 companies. You're going to do this 100 times. It takes a long time to draw this for 100 companies. As long as it takes one, multiply it by 100. Well, there's an easier way, as you can imagine, to find the derivative at a particular point. And when we do this, we're actually trying to find the derivative at any point on a line. Now, if we start with the function here, f of x is equal to 4. If we were to graph this, just a little reminder, of course, that in this case y equals 4, the y value is constant, like we mentioned in the first class, and that's going to be a horizontal line. Well, we know that the slope of a horizontal line is 0, right? The y value never changes, so it's, in this case, it's going to be 4 minus 4 over 1, 0 over 1, so the slope or the derivative is going to be 0. Now, if we do the line, or the function f of x equals x minus 1, well, from here we can tell the derivative just by using the slope-intercept form, right? Y equals mx plus b. The y-intercept must be at minus 1. Slope here, it's not written, it's simply 1. Mx, slope is 1. That must mean that the derivative then, since the derivative is the slope, the derivative is equal to 1 with this function. In class, or excuse me, in the video in the other day, we looked at x squared, and we went through that process and discovered that the slope, or the derivative, was equal to 2x. Now in the homework that you were supposed to have done for today, went in and said, okay, well, what happens with x third, x to the third, or x cubed? Well, you played around with that a little bit, and in the homework you discovered that it equals to 3x squared. Now, just using these 4, of course, there are a lot of other ones, but just using these 4, we can look at it and say, hey, we discover a pattern. What would this actually be? So if you wanted to find the derivative of the function x to the r, where r represents any number, it's x to any power, how would we do this? Well, if we look at this, we know from looking at the patterns that if we have x to the third here, the derivative is always, in this case, is 2. And when we're doing x squared, the derivative, well, this is the same thing as x to the first power when we're working with this. And here, x, and then the x's disappear. Well, what's happening, actually, is that this is the same thing as x to the first power. Oops, that's drawn over a little bit too far there. And the first derivative, the derivative when we look at it, that's the same thing as saying it's x to the 0 power. Anything to the 0 power equals 1. So, even here we see that it is consistently this way, that whenever we're doing your x's, it's going to be x to some power. From looking at the pattern, from 3 it's 2, from 2 it's 1, from 1 it's 0, and okay, well in that case then it must be 1 less than the power you're starting with. So if you're starting with r as your exponent, the power, or the exponent, is going to be r minus 1. Now, sometimes there's a number in front of the x, and hopefully we can also see that when we're working with that. We notice that it's a 3, a 2, and then a 1. And if we look over here, we see, oh, well, yeah, in the original function, the power was to the third, the power was to the second, and this one, the power was to the first. So then that must also be true. So if the power is r over here, this value must simply be r. So we find a little short formula just by looking at the pattern from these, But if you take the derivative of some function, namely x to the r, the derivative is going to be equal to, you take the exponent, the power, and multiply that by x to the, and then take the number of the power and subtract 1. So it's not difficult to do. And as you can imagine, if you had to do 100 of these, would you prefer to graph 100 of them or simply use this formula and come up with 100 answers? Obviously, it's much easier, much faster. Now again, this is referred to as the power rule in calculus. You have some function is equal to x to the r. The derivative is equal to r, the exponent, times x to the, and the power of x is reduced by 1. So if we were doing this function, well, we look at this and say, if we use the slope-intercept form, again, this y is equal to mx plus b, we realize, well, the slope here, in this case it's not written, it would be 1, so that the slope, which again we said is the derivative, is going to be equal to 1. Now we could also look at this on a graph and say, yes, if we graph it, the slope, the change in y, here the y-intercept across is at 6. It's going up, so it's positive. It goes up this point here because the change in y is 1, the change in x is 1. So yes, the slope is 1. If we work at using the power rule, then we would simply want to say that the first derivative, or the derivative, f prime of x is equal to, we realize again that this is actually 1x to the first power. So, well, we don't need the 1, I guess, with taking this method, but it's x to the first power. So we're going to take the exponent of 1 multiplied by x, and then we take the exponent again, the 1, and subtract 1 from it. Well, of course, that's going to be, we don't need to write the 1. That's going to be x to the 0, and we know that anything to the 0 power is equal to 1. So the first derivative, the derivative here, will be equal to 1. Now, you say, well, Greg, you just simply took this x to the first and you ignored the 6. Well, why did you do that? Well, with the 6, what actually happens when you take the derivative, now it's written a little bit high there, when you take the derivative of a constant, of just a number with no x's, what actually happens is the derivative of any constant, whatever it may be, is simply 0. So I'm adding 0 to this. Well, of course, anything plus 0 is going to be equal to what you started out with. So, in essence, when we take the derivative of a function that has a constant in it, you just ignore it. You don't have to do anything with it. We know technically it equals 0, but we just don't need to even write it. Everyone understands this. Now I say, well, why doesn't that affect anything? Why does a constant not change the derivative? Well, again, remember, the derivative is the slope. And here, on the graph again, I have this f of x equals x plus 6, the blue line. And down here, I've graphed just f of x equals x without the plus 6 on it. And you notice that they're parallel. The slope is going to be the same. All the plus 6 does in the original function is simply move this red line up 6 units to here. So when you do that, the slope does not change anywhere on this line. So because of this, that's why we know that if you take the derivative, if there's a constant in it by itself with no x's, you just ignore it, or say that it's equal to 0. Now, getting this a little bit more complex with the power rule, if we were going to do f of x equals x to the 5th plus 364, if we wanted to take the derivative of this, let's say that f prime of x, what we're going to do first is look here, everything centers around this 5. And so we realize that that's r, so it's going to be 5, we take it from the exponent, times x to the 1 less power than it is, or 5 minus 1. Now, technically, after that we had the constant, so we can, again, say that it's 0, but we don't have to write that all the time. And now we look at this and say, well, this is going to be 5x to the 4th. So the derivative, f prime of x, is going to be 5x to the fourth. Now here we have a function, the fourth root of x. Now, how do we take the derivative of this? You say, well, oh boy, it doesn't quite fit the form of x to the r. And you say, well, if we use our log of exponents, yes, then we can get it into the form we need. Whenever we take the derivative, we have to get the original function into the form of x to some power. And to be able to use the power rule, then we have to use our laws of exponents and make it into the form of x to some power. Since this is the fourth root of x, what's that going to be? Well, we know it's going to be x, and if we remember from earlier that the fourth root, I should say it's x to the first power, so the power stays on the top as the numerator, and then the denominator, or the bottom number, is the root that it is. So it's x to the 1/4. Now it's in the form that we can use. F of x equals x to the 1/4. So our f prime of x is going to be equal to, well, the exponent is here, this 1/4. So it's going to be 1/4 or 1/4 x to the, we subtract 1 from the 1/4. We reduce the power by 1. 1/4 minus 1. Well, probably putting it in a form that's more helpful, we would put it as x 1/4 x to the 1/4 minus 4 over 4. Just change 1 and put it into a form that's helpful in solving the equation. So then, when we do this, we get 1 over 4 x to the minus 3 over 4. Now, if you're just finding the derivative, leaving the answer like this is often fine. If you actually have to find a value at a point, or put a value in for x, then of course you'll want to convert this x to the minus 3/4 into the form that you could use. And if we needed to do that, we'd say that it's 1/4, 1 over x to the 3/4, which then is going to be 1/4 times, I should put parentheses here just to make it a little bit clearer, 1 over x to the third, and we take, oops, the fourth root of that. So we would get 1 over 4, the fourth root of x to the third power. So if we needed to use it, we would want to use this form, but if we don't need to use it and just simply recording what it is, this answer would be fine, and obviously it takes less time. Now, here again is another situation where we need to convert this over. So we would say this is the same thing as 1 over x to the 1/4. The 1 is with the x, it's on the top, it's the fourth root, so we put that on the bottom of the fraction, or the denominator. And we're not done yet, so it needs to be in form of x to the r, not 1 over x to the r. So we realize that this is the same thing as x once we flip the fraction over to the minus 1/4. So if you want to take the first derivative, excuse me, f prime of x, now we take again the exponent, it's minus 1/4, and x to the minus 1/4 minus 1. Again, probably putting this in a form that's more helpful, as in 4 over 4. Then we say, oh, all right, that makes it easier. It's going to be minus 1/4 x to the minus 5 over 4. And we have the derivative of this function. Now, I said about not converting it over. When we got to the answer here, I just simply stopped. Well, and that works fine when you're taking the derivative, but sometimes you have to find a value. And that's what we're going to do a problem on here. This is actually relatively easy. That's just simply combining what we just learned with something that we've done in the past. Find the derivative of f of x at the designated value of x. So that means we want to find the derivative, in this case, of x to the fifth minus 1, and find the value of it, what the slope is, what the derivative value is at x is equal to minus 2. Well, this is simply a two-step procedure. when we do this, we need to find what f prime of x is, what the derivative is. Well, we start with x to the fifth, and we did this before. We know it's 5, x to the 5 minus 1 power. Again, plus 0, but we don't really have to write that. So this becomes 5x to the fourth. Now to find the value of the derivative at x is equal to minus 2, what we're going to do is simply use this minus 2 and do an f prime of x. An f prime of x at 2. And if we're going to do that, then we simply do an f prime of 2. So now we use the derivative that we found, 5. Every place there's an x, as you know, you put in a 2. So this is going to be 5 times 2 to the fourth. 2, 4, 8, 16. Multiply these together, and say the value is 80. And it works this way. Doing the same thing, finding the derivative at a specific x value at a point. If we wanted to find the derivative of f of x when it equals x to the 5/4 and find the value at x is equal to 16, what we need to do is to find the derivative. So the derivative will be, again, we take the exponent here, or r, and 5/4 times x to the 5/4 minus 1, in this case 4/4. So when we're doing this, this then becomes 5/4 times x to the 1/4. Now again, we do an f prime at 16. So that's going to be 5/4 times 16 to the 1/4 power. Well, 16 to the 1/4 power, the exponent, the top numerator stays with the 16, so it's 16 to the first power. The denominator, again, is the 4, so it's the fourth root. So 5/4 times the fourth root of 16. Well, we know that 2 times itself 4 times is 16, so it becomes 5/4 times 2, which of course is 5/2. So again, simply taking the power rule that we just learned and then doing something that we know how to do, putting a value in for x for a function, in this case, the derivative function. Now, to make it just a step harder, find the equation of the tangent line to the graph y equals f of x at x. We were finding a value. Now, this time what we want to do, instead of finding the value there, we want to find the equation of the tangent line. Well, the equation of the tangent line, of course, is going to be a function itself, an equation. Now, when we do this, there are 3 steps that we want to do. If we want to find the value of an equation, we know we can use the slope-intercept form, but we need to know the y-intercept for that, and we don't know that in this case. So the other form that we use, again, is the point-slope form. So for that, we need to find a point. So that's what the first is. In the original function, in this case the x cubed, we have a point. We know that it will go through x equals minus 2, and if we do an f of minus 2 in here, then we will find out what the y value is. So we have our x value already, and by doing that we get a y value. So we can do that first. And f of minus 2 is going to be minus 2 to the third power. Now, since it's minus 2 to the third, we know that it's going to end up being negative. A negative times a negative times a negative is a negative. And then 2 to the third is 2, 4, 8. So the value is minus 8. The second step, we need to find the derivative. So we will calculate the derivative. F prime of x is going to be, well, again, we work with the exponent here, the 3, so it's 3x to the 3 minus 1, so it's 3x squared. Now, we want to find the slope. Well, this is the slope at any point. To find the slope at f prime of, at x is equal to minus 2, we do an f prime of negative 2. So we use what we just created, this 3x squared, and it becomes 3 times 2 squared. Well, of course, that's 3 times 4, which is equal to 12. So now we have our slope, or our first derivative. The point that we had, we created earlier here with these two numbers. The x, whoops, we'll have to write the x. The x is minus 2, and the y we calculated here is minus 8. So now we have our point and our slope. So we use our formula. Y minus y sub 1 minus 8 from the point equals our slope of 12 times x minus, in this case, a minus 2. So when we do that, of course, y minus minus 8 is y plus 8. It's going to be equal to 12 times x plus 2. Excuse me, the board is off there a little bit. So we get y plus 8 is equal to 12x plus 24. So our y is going to be equal to 12x, and we subtract 6, or excuse me, 8 to get 16. So that's our answer. The equation of the tangent line will be y is equal to 12x plus 16. So it's, again, applying what we've already done to something that we've done in the past. Now, find the equation of the tangent line. Let's do another example. With this one, f of x is equal to 1 over x, and we're doing it at x is equal to y. So we need to find a point. And of course, that's relatively easy to do. If x is equal to 1, to find the y value, we do an f of 1. So we put 1 in for x, it's 1 over 1, which is 1. So the point, the x is 1, the y is 1, the point is 1, 1. Now, to find the derivative, we need to first put this in a form that we can use. 1 over x becomes x to the minus 1. Now, the exponent is minus 1, so it's minus 1 times x to the minus 1 minus 1. Or, of course, we don't need to write the minus 1, we just need to write the minus. It becomes minus x to the minus 2. Just remember this when you get here, don't get confused by the two negatives. Minus 1 is minus 2. And now we do an f prime at 1, so we use what we just discovered or found here. So it's minus. Now, when you're doing this, be careful. When you're doing this, the exponent here, the minus 2, just goes with the x. You don't apply it to the negative side. So it's minus, you put the 1 in parenthesis to the negative 1. Well, 1 to the negative 1 means you flip it over. So it becomes 1 over x squared. And of course, don't forget the minus sign here as well. So it's minus 1 over 1 squared. Of course, that's minus 1 over 1, which is minus 1. So now we have the slope, and we can use the point slope form. Excuse me. So y minus 1 equals the slope, or the derivative, times x minus 1. As we do the algebra, the problem works out, and we get the slope of the tangent line at this point to be y is equal to minus x plus 2. Now, when we're doing this, what is actually happening here? These three steps. Well, if we find the value at x, and we're going to end up using the point slope form, right? So the value of x, we already know. So if we're going to take the derivative at some point, and let's just call it a, well, x sub 1 will become a, right? And y sub 1, well, that's going to be the value that we get when we put a into the function. Well, the calculus way of saying that is that you're doing f of a. You put in a for x and find what your answer is. So to make this formula more calculus-based, so to speak, we can substitute these two things in. And we remember that the slope is also the derivative. So if we're going to continue this theme, the slope, or our m, will also be equal to f prime of a, or f prime at a, the derivative at a. So the calculus form of the point slope formula is this: y minus f of a equals f prime of a times x minus a. So if we want to find the equation of the tangent line using calculus terms, we just use this function. I don't really care which one you want to use. They both do the same thing, serve the same function, just are expressed differently. So you can use the regular equation or this calculus equation of this same thing. Now, there is something called the secant line calculation of the derivative. And when we're working with this, this is not something, I should say, this is something that if you take calculus, you should know or at least be aware of. Since this is business calculus, I'm not going to require you to know it, because using the power rule is easier than taking the secant line calculation of the derivative. However, the textbook will refer to it, so you should be at least aware of what it is. So if you just kind of follow what's happening here, it should make sense, and you'll understand when you see it in other business courses if it comes up. Now, the secant line, if you wanted to find the tangent here of this function, when x is equal to 1, we would do it at this point here when x is equal to 1. And a secant line means that if you have a point on the line, you find another point on the line or the curve, and you draw a line between those two. This is the secant line. And, excuse me. The secant line calculation of the derivative is similar. Okay, start again. The secant line calculation of the derivative is something that's important in calculus, and the book will talk about it. You'll come across it some other times. But the power rule is much easier to use. So I wanted to show you what it is, but I won't require you to use this, just to understand it. That way when you see it in the future, you'll know what I'm talking about, what other people are talking about. The secant line calculation of the derivative at a particular point, let's choose a point here of x is equal to 1. The secant line is made by finding another point on the curve and connecting those two together. This is the secant line. Now you notice that I picked a point further away. And we know that the tangent line is going to be something a little bit high there, but something more like that. So obviously the tangent line and the secant line, this secant line will not have the same slope or the same derivative right there. But we notice that if we move the point closer, it gets closer and closer to the tangent line. So as we move it down, as we get very, very close, in fact we can get infinitely close to this, as we get closer and closer to the original point, eventually it gets closer and closer to the tangent. So we can use this fact, the secant line, to calculate the derivative. What they do with this is, this is a little bit confusing, but don't worry too much about it, it's not too hard. Again, we have point P here, which is the point that we chose. In this case, it's not 1, it's just some value of x. So the point here, even without knowing what the function is at all, the x value is x. The y value, well, it's some function, so it's f of x. We put x into the equation and we'll get our y out, our f of x. The second point that we chose, in this case, to say that it's point Q, any point. Well, what's the x and y values of point Q? Well, x here, let's add h to it, where h means any length. We could pick whatever length we want it to be. well, then the x value is going to be x plus h. X brings us out to here, h brings us out to this line wherever it may be. So the x value is x plus h. The y value, well, what we're going to do is take the function and put x plus h into it. So it's f of x plus h for the y value. And if you think about it this way, this height, or to this point, is the same as over here. So this height is f of x. This whole height, again, we said the y was f of x plus h. If we wanted to work with this, the whole height is going to be x of f plus h. But if this part of it is f of x, to find this part of it, we take the whole value, the f of x plus h, and subtract f of x to get just this. If we wanted to count, to calculate the slope of this secant line that we've drawn here, we do the change in x over the change in y, here over the change in x. And that's what we're doing up here. The slope of the secant line will be the change in y, that's f of x plus h minus f of x, the same thing that's here. Then we're going to do, do it over the change in x. Again, if this is x and this is x plus h, if we use their points, f of x plus h minus x using the slope form, or it's going to be h. Even if we do this, it's x plus h minus x, well, plus x minus x cancels out, and we simply get h. So we get this function for the slope of the secant line, f of x plus h minus f of x over h. Now when you take the secant line, what you're supposed to do is to first calculate the quotient of this that we just found, and then let h get smaller and smaller until it gets down to 0. Of course, it's never going to equal 0 because you can't divide by 0. And we say let it approach 0. And then, as h approaches 0, we get the tangent line. And we can use this formula to find it. Now again, when we did this using the simpler form, we said, well, if we take the derivative of x squared, that's going to be 2x, then we do an f prime of 2, and we get 4, and we're done. So it's much easier, much faster. If we wanted to do this with the secant line calculation, what we do is we use this formula and put 2 in it, since our f is 2. So our x, is 2. So it becomes f of x, which is 2, plus h, minus f of 2, all divided by h. And we put that into this function. So it's x squared. So an f of 2 plus h is going to be 2 plus h squared, because it's f of x squared, minus f of 2. Well, that's going to be 4, right? 2 squared. So we're minus 2 squared, all over h. Now, we let h approach 0. Now, in looking at values of this, this isn't required as part of the secant line calculation, but to see, when h is positive, when it's greater than x, when it's 1 more than x, we would use this particular value that we just got this formula, and find, when we put in a 1 for h, the secant line slope will be 5. As we put in 0.1, 0.1, the slope of the secant line will be 4.1. As we keep getting smaller and smaller and smaller, we see that the values approach 4. When h is negative, and that means h, the other point is less than 1, or excuse me, less than 2 in this case. If we're using an h of minus 1, the point would be on the left side of our original one. We look at the slope, and we do an h of minus 1, we get 3. And as we make this change, the difference between the two smaller and smaller, closer and closer to 0, as it approaches 0, we see that the slope also approaches 4. So that tells us the slope should be equal to 4. And using the general power rule, we know that it is. Now, to make the secant line function work, what we do is we say that the derivative is equal to this, and this simply means, we kind of skipped over this since we won't use it a lot, but we find the limit. What the limit is what this is approaching from both sides, 4. We do as h approaches 0. What we do is we take this, what we just found, and do the algebra, do the math. 2 plus h squared is going to be 2 squared plus 4h plus h squared minus 2 squared all over h. We notice here the 2 squared minus 2 squared cancel out, and we're left just with 4h plus h squared, which is what's here. Factor out an h and divide it by the h that's here, and you get 4 plus h. As h goes to 0, then it becomes 4 plus 0, which equals to 4. So, as you can see, it's a lot, well, I shouldn't say a lot harder, but it's more difficult than using the method I'm teaching you. So be aware this is how it happens. The final step that you're supposed to do then is to say, does this work for any point? In that case, you do the same thing, but you leave the x in as itself. So you go through the same thing. X plus h squared is x squared plus 2xh plus h squared, minus x over h. X squared minus x squared cancels out. Get 2xh plus h squared over h. Factor out the h as we did before and cancel it out. You get 2x plus h. As h approaches 0, it's 2x plus 0, which is 2x. So again, this just takes a lot more steps and a lot more math than the other method. So be aware of it. This is called the limit definition of the derivative. I won't require it for this class, but if you see it, now you have an idea what they're talking about. The homework to be worked on in class, and maybe you want to do some of the problems before you come to class to be familiar with it. And from section 1.3, the red, anytime you see something in red that says challenge, it is an optional homework problem to do. If you enjoy this section or just like a challenge, please feel free to do it, but it would never ever appear on a test or a quiz. It's optional. This is also on Moodle, so you can get it there.